Yes, great. So I see your screen now. And yeah, so good afternoon, everybody. So I'm Juan Bernard. So I'm a software developer in G.tec. So today we're very happy to have our next presentation for the Spring School from Parnian Fazel. I hope my pronunciation is good. Sorry if I mispronounce it. So she is a biofeedback researcher and a teaching assistant in Hamburg University of Applied Science. And today she will talk about the influence of single sections EEG-based neurofeedback on heart rate variability and time perceptions performance. So let's welcome our presenter. Yeah.
Thank you very much. So hi, I'm Parnian, biomedical engineer. I've always been fascinated by how the brain and the body talk with each other. And one thing I've especially been curious about is our sense of time, how we actually feel the time passing and whether that's something that we can train. This study I'll be sharing with you today came out of this curiosity. I combined EEG-based neurofeedback, heart rate variability, and a few cognitive tasks to explore how all of these might be connected, even within a single session. So just to give you a little bit of a summary, we ran a single session neurofeedback experiment using sensory motor rhythm Beta1 training at the CZ channel with the Unicorn Hybrid Black EEG headset. Participants first did a paced breathing task, then two time perception tasks, one to judge speed differences and one to reproduce intervals. We measured EEG peaks during the sessions to see if anything shifted in their timing abilities or physiological states. And the general idea was to find out whether one session could make a measurable difference. So just to give you a little bit of a background, neurofeedback is a technique where we record brain activity with EEG and give the person immediate feedback. It's often as a video or as a video game, reacts to their brainwaves. Over time, participants or users learn to regulate this activity by themselves. The method is grounded in the science of brain plasticity. So our brains can adapt throughout life, and by rewarding desired brain states in real time, we can reinforce those patterns. Clinically, usually it's used in ADHD therapy or epilepsy. Depending on the goal, we target specific brainwave frequencies, for example, in this case, SMR and Beta1, that are often linked with focus and cognitive stability. So it's important to know that people respond differently to neurofeedback. That's why it's personalized, and personalized setups like adjusting the threshold or feedback modalities can make a huge difference in the success. You can see here that the core process kind of looks like this. The EEG is recorded, it's cleaned, the features are extracted and classified, and the results map directly to the feedback the user sees. So it kind of creates a closed loop between the brain and the system. Time perception is, you could say, one of the most essential functions of the brain. It really enables us to estimate durations, we sequence our actions, and coordinate our behavior in routine and demanding tasks. From crossing the street or playing an instrument, it affects almost everything that we do. In cognitive neuroscience, we typically distinguish between prospective and retrospective timing. Prospective timing, it's happening in the moment. You're actively attending to how much time is passing. Retrospective, on the other hand, relies a lot on memory and reconstructing how long something had lasted after it ended. There are some specific models that explain how we internally track time. The number of pulses counted are dependent on attention and arousal. The more attention we pay to time, the more pulses are counted, which then lead to a longer perceived duration. However, when we're under a high cognitive load, fewer pulses get through and the duration seems shorter. That's why in exam times, like once the exam starts and finishes, it feels like it was such a short time. We commonly study time perception using two kinds of tasks, discrimination and reproduction. Discrimination asks whether one interval is longer than another, and it taps into perception and judgment, and reproduction is a bit more complex. It requires memory and motor timing and a sort of internal calibration. On the neural level, time perception is quite distributed. The cerebellum, basal ganglia, and especially the prefrontal cortex are all involved. And for example, the cerebellum is classically tied to millisecond timing, while the prefrontal cortex supports executive control and memory integration. So altogether, these systems allow the brain to maintain a sense of when, not just what or where, and it's a critical dimension for any system seeking to train or modulate cognition. Another topic in the study was heart rate variability. The heart and brain connectivity is far more than just metaphorical. It's the heart and the brain are in constant dialogue via the autonomic and neurohormonal pathways. And this interaction directly shapes how we think and how we feel and how we perform. The key metric in this is something called heart rate variability, or HRV. It captures how flexibly the autonomic nervous system responds to internal and external demands. Higher HRV indicates a more adaptable system. It supports better emotional regulation and attentional focus. And central to all of this is something that maybe you've heard of. The vagus nerve is central in this process. It not only regulates the heart rate, but also communicates the internal state information back to the brain. So this makes HRV an important index of self-regulatory capacity. And something else is paced breathing, which is something that's practiced very often. This boosts the vagal tone and HRV, and studies show that even short sessions of paced breathing improve cognitive performance. What's particularly fascinating for our context is how HRV also influences temporal cognition. There is research using simultaneous EEG and ECG showing that a high HRV enhances the neural mechanisms of time perception. This includes a greater synchrony in the theta and beta bands and more consistent time estimation. Coming to the research objectives, the main objectives of the study was to explore whether a single session EEG-based neurofeedback could impact how we perceive time. We know that multi-session interventions have shown to have cognitive benefits, but there's little evidence on short-term effects. Specifically, we looked at time discrimination and time reproduction, which are both central to our ability to act and to decide in time-sensitive contexts. And at the same time, we measured heart rate variability to see how neurofeedback might influence the brain and body regulation. So we formulated these key hypotheses to guide the study. First, we expected the neurofeedback to enhance SMR and Beta1 frequencies, since these are tied to sustained attention and motor control. Secondly, we hypothesized that the neurofeedback to enhance SMR-Beta1 frequencies. And since we hypothesized that this enhancement would then lead to a better performance. And third, we anticipated that neurofeedback would have a measurable effect on HRV. And lastly, we wanted to see if those individuals who benefited from the neurofeedback more, meaning that they had a greater brainwave change, would also show a better performance in the timing tasks, since this would then indicate a dose-response relationship between neurofeedback efficacy and cognitive gain. So for this study, we used the Unicorn Hybrid Black EEG headset. We sampled at 250 Hz with focus on channel CZ. Cardiac signals were also recorded using a device called the CardioSecure, which then streamed the ECG data from 3 chest electrodes. We built our entire pipeline in MATLAB using the lab streaming layer, Psychophysics Toolbox, and GStreamer. So this is what the environment looked like. We kept the room quiet and dimly lit. We used shielding cabling to reduce the noise, and we positioned the participants, like you can see in figure 4, about 65 centimeters away from the monitor. So the first task was the paced breathing. It was a 7-minute sequence where breathing rates increased from 6 to 18 breaths per minute. A growing and shrinking circle would then, along with alternating tones, then helped with the breathing in and breathing out. And then we had the time discrimination task, which participants watched a ball move at a constant speed behind a occluder and then judged if it came out faster or slower than before. We had a plus minus 300 millisecond change to create this illusion. This is what it looked like up close. This square-shaped occluder that you can see in the middle was filled with a dynamic and randomly generated pixel pattern in each trial so that you could prevent the participants from using visual cues or developing a strategy. We did this to ensure that they relied purely on temporal perception rather than memorizing any visual reference. In the time reproduction task, we showed a brief visual interval appearing 3 times. They randomly had an interval between 1 to 3 seconds, and participants were then asked to reproduce this interval for 30 seconds by tapping the space bar. So they had to stop themselves after what, based on their estimation, 30 seconds were over. So to start the neurofeedback, we measured a 30-second baseline of the SMR-Beta1 at CZ, and we calculated its peaks. And then we calculated the peak ratio over neighboring bands and set 80% of that as the individual threshold. This is what an example of it looks like. During the actual training, a video would play, and it would only continue playing if the participant's SMR-Beta1 stayed above that threshold. Otherwise, it was paused. The audio continued just so that we could reduce frustration and keep the engagement with the video. And this loop then lasted 25 minutes. It was updated every second using FFT. So final point of methodology. We processed all the data in real time. All the tasks were saved. The EEG was streamed into MATLAB in real time using the lab streaming layer, which really allowed for the video feedback to respond. live to any of the SMR and Beta1 wave changes. We also logged the second per second video playback status to track how long participants maintained their brain activity above their threshold. Now, coming to the results, for the neurofeedback threshold setting, we set the maximum SMR-Beta1 peak during this 30-second baseline recording, and then calculated the 80% of that. Here in this figure, you can see how it was for each of the participants in their individual thresholds. You can see that some of the peaks varied, some increased, some declined, but mostly they remained stable. We applied, for simplicity, the 80% rule to all of them. And the CMs that we recorded indicated moderate variability and actually no outliers. If we take a look at the neurofeedback performance itself, you can see here the individual plots. The solid blue line indicates the peaks, the SMR-Beta1 peaks, and the dashed line is their threshold. And whenever the participant crossed the threshold, the video continued playing. So that is showed in the green bars on top. And as you can see, most of the participants, like participant 2 and 3 and 6, they showed clear improvement towards the end in sustaining their video on time. And some participants, like participant 1, couldn't quite make it work, but we'll come to the possible reasons for that in a minute. Here we can see the HRV power log values across the different breathing rates before and after neurofeedback. As expected, the power decreases as breathing becomes faster in both of the cases, but what's interesting is that the post-neurofeedback curve stays slightly elevated at some high range rates. This might suggest a subtle improvement in vagal tone and autonomic regulation. The trend isn't dramatic, but it aligns with the idea that neurofeedback enhances physiological balance. This is also from the HRV. It's, however, the RMSSD is a different calculation. Across the breathing rates and post-neurofeedback levels were slightly more stable at higher rates. This also suggests a improved autonomic resilience. Taking a look at the psychometric curves for the time perception tasks, this is for the time discrimination task before and after neurofeedback. On the x-axis, we have the time difference in milliseconds. So it was plus 300 millisecond and minus 300 millisecond. And on the y-axis, we see the probability from 0 to 1 of the participant judging the ball as faster. So the steeper the curve, the more accurate the results of that particular participant. So we can see that post-neurofeedback, the curve is steeper, meaning that the participants were better at distinguishing small differences in time after the session. And so they had an increase in temporal sensitivity. Also, if we take a look at the shading or the shaded area, which represents variability, the post-neurofeedback curve has a shrunken shaded area, and this suggests that performance also became more consistent. So in the time reproduction tasks, we can see this result. The figure shows that the mean absolute error for each participant had a reduction after the neurofeedback session, meaning that they were more accurate in reproducing the time interval that was given to them. So coming up with the key findings, we observed that a single session EEG-based SMR-Beta1 neurofeedback enhanced temporal processing precision. This was then reflected in a steeper psychometric function for time discrimination and a reduced mean absolute error in time reproduction. These findings also support the modulation of the internal clock through oscillatory upregulation. And although we did see the HRV parameters show an improvement, they had no statistical significant change, so suggesting that autonomic entrainment via the cortical modulation may require multi-session protocols or perhaps a more integrative approach. So we could show that the unicorn hybrid black EEG paired with LSL enables low latency and real-time neurofeedback capable of really modulating SMR-Beta1 activity. It really allowed a seamless integration of L into MATLAB to allow for a precise connectivity. And if we take a look at single CZ channel, it perhaps constrained the spatial resolution. While it was effective for cortical self-regulation, the limits of it really limited the full brain insights. Additionally, LSL bandwidth and hardware resource constraints restricted spectrogram logging. And perhaps for future systems, it can be suggested, or they would really benefit from dynamic thresholding and multi-channel acquisition to fully exploit what the g.tec ecosystem is capable of. So this brings us to the end of my presentation. Thank you so much for your attention. I'm really looking forward to your thoughts, whether it's about the unicorn EEG or the LSL integration or any part of the neurofeedback setup. Feel free to connect with me, and so that we can discuss the conversation beyond what I explained in this session. And also, if you're interested in getting access to the sources or the bibliography that we use for the study.